Okay, welcome back. We're going to be looking at a different problem with friction today. The problem says a box of mass 8 kilograms is pushed with a force of 20 newtons. The coefficient of kinetic friction on the surface is 0.23, and we are to determine the acceleration on the box. So, as we've talked before in class, our problem solving strategy is always to identify different bits of information that are important. So, I'm just circling some numbers that immediately pop out to me. And then I'm going to underline some things that might be important. So it says mass is 8 kilograms, force is 20 newtons, and then the coefficient of kinetic friction on the surface is 0.23. So I'm going to go ahead and use my problem solving technique that I always use. Let's go ahead and write these down as variables off to the side. So mass, in this case, is 8 kilograms. We know that the force, in this case, it's pushed with a force, so that's going to be the applied force, is equal to 20 newtons. All right, the coefficient of kinetic friction, so that's mu sub k, is equal to 0.23. And then it says determine the acceleration on the box. So acceleration is unknown. All right, so those are our givens. Now we got to find our relationship. And sorry about that, I had a child toddle in and ask a question. So we've gone ahead and put our variables over here. Now we want to go ahead and determine the relationship between these variables and what we want to find. So that's acceleration. So I think what would be most beneficial is we just kind of need to draw a free body diagram. So we're going to do that by drawing our box on our surface. I'm going to change my color just so that we can kind of see what's going on. We know that gravity is pulling this object down, and the force of gravity is equal to the mass of the object times the acceleration due to gravity, mg. We know that the normal force is pushing the object back up. Those are equal and opposite because the object's not accelerating through the surface. We know that the applied force is in this direction because it is positive x. So it's going to be going that way. And we know that the frictional force is going to be smaller than the applied force. And that is going to be the force of kinetic friction. So it's F sub K there. All right, so that's a general diagram that's going to help us to build now a force-net equation, because what I'm really seeing is that the net force here is going to be equal to 0 in the vertical. So that's not important. What we really want to talk about is the net forces side to side. So net force, in this case, F net, is equal to the applied force, FAPP, and then it's going to be minus the magnitude of the force of friction, kinetic friction. Okay, well that's a relationship, but does it get us any closer to these things over here? Well, I know that force net is actually just Newton's second law, and so that equals mass times an acceleration of an object. So if I know the mass of this object and I know its acceleration, I know the force net. Likewise, if I know the force net and I have one of these other two, I can find the third. That's then equal to the applied force. And then friction, the kinetic friction here is going to be equal to mu sub k from our previous formulas times the normal force, which in this case the normal force is equal and opposite to mg, so we're just going to call it mg. All right, now we've got some variables that may look very similar to what we have over here. Do we have m? Yeah, we got m. Do we have a? No, but maybe we can find it. Do we have FAPP? Yes. Do we have mu sub k? Yes. So it looks like the only variable that we're missing at this point is indeed the variable we want to find, which is a. So let's just go ahead and start plugging in these numbers. Okay, well if that's the case, mass equals 8. So we've got 8 kg times acceleration is equal to, the force applied was 20 newtons, minus, I'm going to put this in parentheses to make it a little bit easier because we don't want to get our order of operations all messed up, 0.23 was our mu sub k, times the mass of the object, which is 8 kilograms again, times the acceleration due to gravity, g, which is 9.8 meters per second squared. Okay, well, that's a lot of numbers. So let's compress those down. Let's go ahead and figure out what those are. I'm going to start dropping my units just so it's a little bit easier to see. But basically what that means is all the stuff on this side is going to be equal to 20 minus, when we do this in a calculator, we would find that this is approximately, not exactly, but very, very close to 18. It's actually 18.003. So we'll call it 18 because we don't need that level of precision. So 20 minus 18, that's going to be equal to 2. So 8a on this side equals 2. We move that 8 over. A is going to be equal to 2/8, which is the same thing as saying that in this case, acceleration is equal to 0.25 meters per second squared. Now, does this jive with what we expect? Does this fit with our expectation? Well, first off, look at the diagram. We know that force applied is bigger than the force of friction because it says the object is accelerating. We're determining if the object is accelerating. So we expect it to. Okay, well, then we should get some sort of positive value because it's going to be accelerating in the positive direction. We know if the object's moving, the net forces are not equal to 0. We solved that. We then came up with an equation that utilizes all the stuff that we know. Our formula right here is basically just the friction formula for kinetic friction. And then we put in our numbers. We solved the equation, and we found that the acceleration on the object is exactly 0.25 meters per second squared. So if you were to approach a problem like this in the future, again, what we're going to do is we're going to pull out our variables. We're going to figure out what we got. We're going to draw ourselves a diagram. We're probably going to set ourselves up a force net equation that's going to let us compare one thing to another. There's likely going to be a friction component, which is going to look something similar to this, whether it's mu sub s or mu sub k. And then you're going to see these similar values. Usually force net is going to break down somehow into mass times acceleration, unless it's given in some other fashion. But this just gives you a little bit more idea as to how to approach that particular style of problem. If we were looking for mass, of course, mass would be the variable that we would isolate. If we were looking for any other variable, it could be the applied force, we would isolate that particular variable by itself as well. So that's how you approach those sorts of problems. All right, good luck with your problems. They're waiting.